convert it to energy. Rest mass has some energy associated with it. So if you appreciate, in this course we are looking at the very fabric of our universe. What makes us, what makes our bodies, what makes our surroundings, what makes air, what makes the planets, what makes the earth, how do we receive energy from stars and from the sun. So we are looking at the very fabric of the universe. So it's a very fundamental undertaking that we are involved in. And as you will also realize, either in this course or when you study on your own, is that the concepts that we learn walk into the sphere of philosophy as well. So physics, as you know, when Newton wrote his famous book, what was the name of the book? In the 17th century, what was the name of his book? The book was named The Principles of Natural Philosophy. So there was a time when physics and mathematics was called natural philosophy. That is the philosophy of nature. So when we're studying these concepts, they are so bewildering concepts, they are so surprising and counterintuitive concepts that they often walk into the realms of philosophy. And there are some universities that offer degrees in the philosophy of physics. So you must realize that you are doing a very noble task. You are involved in a very noble task of understanding your own origins, what makes you the way you are, what makes you think the way you think, and so on. So we'll continue our discussion of matter and energy. And just a brief recap of what we've done so far in the 4 or 5 lectures that preceded today. We looked at the idea of Planck. And what was Planck's major contribution? If you could summarize this, what was the major contribution of Planck? Energy is quantized. Something more accurate? The energy is quantized because the atoms that make up the walls of the cavity, their motion is quantized. That's what Planck showed. The atoms that make up the wall of the cavity, their motion is quantized. Their energy is quantized. And when there are transitions from one energy to another, that energy is transmitted into the cavity. That was Planck's contribution. Then entered Einstein. And what was Einstein's contribution? If you just want to summarize it in a sentence or two. Right. Einstein showed that radiation is also quantized, and its radiation comprises packets of energy which he called photons. That was Einstein's contribution. So this is the year 1900, the year 1905, and Compton. In 1923, he performed these monumental experiments. And what was Compton's major contribution? Compton की contribution क्या थी? आप बताइए, आप ब्लू शर्ट में, डीप ब्लू शर्ट में. Photons have momentum. That was Compton's contribution. Photons possess momentum. So Einstein showed that photons indeed have energy, and the energy comes in packets. And Compton went a step further and showed that the photon has a momentum. And the momentum, of course, is a vector quantity. So you get angular dependence on the wavelength shift. And that is what we learned in the previous lecture. So this is what we've done so far. Now we're going to extend this concept a little further, move back in history a little bit, and see that all matter is made up of particles. There's a particulate nature of matter. And what do we mean when we say a particle? Particle का लफ्ज जब हम कहते हैं, हमारे ज़हनों में क्या तस्वुर उभरता है? जी बताइए.
That it has a mass.
It has a mass and a volume. It has some spatial extents. It has a mass, it has a volume, you can touch it. This is what a particle really is. Something that has mass, something that has a spatial extents, some thing that is grainy. Something that is grainy. जिस तरह रेत के जर्रे हैं. That is what a particle is. Something that has a graininess to it. It's not a continuous fabric, but something that is grainy. In fact, this idea dates back to the early Greeks. Before Christ, Democritus and Leucippus, they presented this idea that matter is composed of small particles, and those particles, they were called atoms. What is the origin of the word atom? What does atom mean? किसी को पता है? Indivisible. Because tom means to cut. Tomography means to cut and see. Tomography. ठीक है? Anatomy. Anatomy में जो tom है, TOM, means to cut. Ana means to build. Anatomy, to build and cut. That's what anatomy is. And this A, इसे prefix कहते हैं साबिका. This means, this comes as a negation. Something that cannot be cut. That's what an atom is. So up till the 20th century, it was believed that atoms are indestructible. They cannot be divided further. And that's the smallest particle that can be seen. Now there was a large number of experiments performed that showed one after the other that matter is indeed made up of particles, atoms, ions or molecules. And a large number of chemists contributed to this. For example, the French chemist Lavoisier, he came up with the idea of the law of conservation of mass. That mass is conserved in a chemical reaction, which means that particles that entered a chemical reaction, they had a certain mass, and particles that left this chemical reaction, they had a certain mass, and mass cannot be created or annihilated or destroyed. So the idea of particles or the idea of the fundamental constituents of matter was gaining grounds. Then we know that Dalton, he formulated an atomic theory, and he also formulated the concept of partial pressures. Right? So partial pressure means that gases have particles, and the higher the number of particles, the higher will be the pressure exerted by that particular gas. You remember the Dalton's law of partial pressures. Then we have the chemists Gay-Lussac, that all gases of the same number, one mole of all gases have the same number of particles. Then came Avogadro. Avogadro showed that one mole of all objects, of all elements or compounds, they have the same number of particles. Therefore, the idea of particles was gaining momentum. That all matter is fundamentally constituted of particles. The exact nature of those particles, whether they are atoms, ions or molecules, that was also under consideration and investigation. But you see, there's a course in history that the evolution of science follows. And one of the most important experiments which we can trace back were performed by Michael Faraday in 1833. And he was able to perform what is called, in modern terms, electrolysis. So what happens in electrolysis? This is a very light review of the history of science. So, and most of you already know this from your FSC or from your A levels or your previous education. So I'm going to be fast, but it's just a lightning review of what was happening in 1833 and how does it relate to the course of modern physics. In electrolysis, what Faraday had was molten sodium chloride. And what he basically did, he had two electrodes and these electrodes were connected to a power supply and a galvanometer which could measure current. We also had some kind of some device for measuring the time. And what really happens in this experiment is that the sodium ions, which are positively charged, they move towards the cathode. They move towards the cathode. They move towards the cathode. They pick up an electron provided by the battery, and sodium metal deposits on the cathode. So electrodeposition takes place. And what happens on the other electrode, that is the anode, is that the chloride ions move towards the anode. They leave, they give up their electrons to the electrode, which then flows through the external circuit and constitutes a current, and two chloride ions, after donating their electrons, they recombine and form chlorine gas and go into the atmosphere. So this is the basic scheme of an electrolysis experiment. So what Michael Faraday did was he measured the mass of the electrodes before the electrolysis and allowed the reaction to take place for a prescribed amount of time, measured the current I. So the charge flowing through the circuit for time t is given by IT. And what he did, he measured the mass of the sodium deposited. That is, he took out the electrode, measured the mass of the electrode with the deposited sodium, and from the difference calculated the mass of deposited sodium. And he found out that whenever the charge that went through the circuit was about 96,500 coulombs, 23 grams of sodium was deposited. Right? So this unit of charge is called the Faraday. So if the same reaction was allowed to proceed for half the time, half the charge was flowing through the circuit and half the mass of sodium, it is 11.5 grams of sodium was deposited. If you repeat the experiment with potassium chloride, 40 grams of sodium would be deposited when this amount of charge flows. So what does this experiment show? This experiment shows, first, that ions exist. Second, charges exist. Third, charges exist as integers. Repeating the experiment with barium chloride would give you a different scenario, because barium now has a valency of 2+. It will accept 2 electrons and 1 mole of barium would be deposited. So when one Faraday of current flows through the circuit, the atomic mass of barium is 137. 137 divided by 2 grams of barium will be deposited. So this experiment was the beginning of what we could say the concept of the quantization of charge, and that charge really exists. There is no other way to explain electrolysis and the liberation of chlorine gas or the deposition of sodium metal without invoking the concept of valency and charges. So now we know that charges exist. Now let's move another 60 years ahead. देखिए ये 2011 है, तकरीबन 100 साल पहले अगर तसव्वुर करें कितनी रैपिड एडवांसेस हो रही हैं साइंस में, ठीक है। 1896. In 1896 में J.J. Thomson was performing some revolutionary experiments, and he formulated the fact, and he discovered the fact that electrons exist. So it was known that charges exist through Faraday's work on electrolysis. Now Thomson was looking at the very heart of matter, and for the first time he was able to see the subatomic world. Atom के अंदर भी कुछ है. He was able to see the subatomic world, and mankind was able to look into the inside of the atom, and the atom was actually destroyed. ठीक है, J.J. थॉमसन का काम देखें. चार्ज की क्वांटाइजेशन का पता चल रहा है हमें केमिस्ट्री से, वैलेंस से, इलेक्ट्रोलिसिस से. अब थॉमसन एक कदम आगे रखता है और बताता है कि इलेक्ट्रॉन्स एग्जिस्ट करते हैं, एंड दोस इलेक्ट्रॉन्स आर क्वांटाइज्ड, देयर चार्ज इज क्वांटाइज्ड, दोस इलेक्ट्रॉन्स आर इन फैक्ट पार्टिकल्स. दिस इज व्हाट थॉमसन was doing at the turn of the 20th century. In the same year, 1896, the same year, radioactivity was discovered. Henry Becquerel. So radioactivity में क्या है? The nucleus disintegrates. Even though the nucleus was not known at that time, but there was some radiation coming out of atoms. The atom had been broken. In the same year, 1896, Wilhelm Röntgen had discovered X-rays. देखिए, 1900 में Planck's ideas came into existence. 1905 में Einstein had presented the concept of Brownian motion, which also showed that matter comprises particles. So all of these events were happening at the turn of the 20th century. जब 20th century का आगाज होता था. तो जरा J.J. थॉमसन के काम को देखते हैं. So these are very exciting times for physics or for science. So what did Thomson really do? Thomson really showed that electrons are a universal particle. They belong to all matter. All matter, whether it's hydrogen, lithium, boron, oxygen, carbon, sodium chloride, any compound that you can think of, any element known at that time, there are also going to be electrons, always going to be electrons. By the way, I remember in the year 1896, Mendeleev also presented the periodic table. So these are very exciting times. Alright, so let's look at Thomson's discovery of the electron and see what experiment did he perform. So Thomson's experiment is quite a beautiful experiment in which he had a glass tube similar to the tube that we use in cathode ray televisions and oscilloscopes and computer screens, old computer screens. This is a glass tube which can be evacuated. So you can take gas out and you can put gas in. So there is a low pressure gas inside the tube, a very low pressure gas. It could be air as well. And then there are electrodes. There is a negatively charged electrode connected to the negative terminal of the power supply, and there are anodes which are constructed in the fashion of slits. So these are positively charged plates, So these are anodes made in the form of slits, and this screen is coated with a phosphor coating such as zinc sulfide. It's a phosphorescent material. What is phosphorescence? क्या होता है phosphorescence? So when an electron or a charged particle strikes a phosphorescent material, it emits light. And what's the difference between phosphorescence and fluorescence? Phosphorescence lasts for some time, even when the charged particle or the ionizing radiation has gone away. ठीक है? थोड़ा सा ग्लो रहता है phosphorescent material में. Fluorescence में ऐसा नहीं होता. So this is a zinc sulfide screen, and one also has electrodes here, and you can apply an electric field between these electrodes. So this is a parallel plate capacitor. So what J.J. Thomson did was that when he turned on the electric field, when the electric field was switched off, a glow was seen in the middle of the phosphorescent screen. That is, some particles or some rays had gone straight through and hit the center of the screen. अब देखो ये एक्सपेरिमेंट्स थॉमसन से पहले शुरू हो चुके थे और इनकी एग्जैक्ट इनकी नेचर पे बहस हो रही थी कि वेदर waves are being emitted or whether particles are being emitted. Okay? Ab Thomson set the stage and he showed that in fact these are particles which he called electrons. So when no electric field was superimposed, the particles or the electrons hit A and this region glows. If an electric field is superimposed in the direction that I've shown, you get a glow somewhere here, which means that the particles have actually been attracted by the positive electrode and moved downwards. Their trajectory has shifted and this region phosphors, which shows that these waves or particles, whatever they are negatively charged. Okay? Now what Thomson's major contribution was that he measured the charge to mass ratio of these particles. He measured the charge to mass ratio of these particles. And no matter what gas he uses inside the discharge tube, the charge to mass ratio always remains the same. Whether he uses nitrogen, argon gas, nitrogen, oxygen, air, whatever he uses, the charge to mass ratio of these particles remains unchanged, which means that these particles are a fundamental constituent of all kinds of matter. ये थॉमसन की मेजर डिस्कवरी है, and he called these particles electrons. So how does one really find the charge to mass ratio? It's a very simple exercise in mechanics and electrodynamics, and I think you already know about it. Alright, so let me ask you how to do it. So the particles have a speed Vx when they enter the region between the plates, and when they emerge from the plate they have a velocity v with the horizontal component Vx and a vertical component Vy. Will Vx change? Vx will not change, whereas Vy will increase under the action of the electric field. Alright, so could you tell me what Vy would be? If we draw a close-up of the same setup, we have these plates. The distance between these plates is suppose small d. The length of these plates is capital L. At this point, the velocity makes a certain angle with the horizontal. That angle is theta. It's a small angle, and this is Vy, and this is the resultant velocity. The electric field is pointing in this direction, it's E. So what will Vy be equal to? बताइए. तो उसको हम ये बताएंगे इलेक्ट्रिक फील्ड की टर्म्स में देखते हैं. मास नहीं आते हैं इलेक्ट्रॉन के. You want to find the charge to mass ratio. This is a very simple problem. There is a force acting on the electrons. There is an acceleration on the electrons. You can find the final velocity. ठीक है. देखिए बहुत आसान है ये. तो Vy is the acceleration in the y direction times the time. The initial velocity in the y direction is 0. So the acceleration in the y direction is given by force over mass. The force is E, capital E, mass of the electron is m. And what is time? The time for which this force is acting is actually distance L over Vx. Okay? And what is the electric field? The electric field is simply the voltage divided by the separation between the plates. So this is the final velocity in the y direction. But do we know the initial speed in the x direction? Or the uniform speed in the x direction, Vx? No. हमें Vx तो नहीं ना पता. हम E over m फाइंड करना चाह रहे हैं. वोल्टेज अप्लाइड पता है, डिस्टेंस बिटवीन द प्लेट्स पता है, लेंथ ऑफ द प्लेट्स पता है, Vx नहीं पता. तो हाउ डिड थॉमसन फाइंड आउट Vx? देखो एक्सपेरिमेंटर का माइंड बहुत करिश्मा होता है कुदरत का, कि वो अभी देखता है कि मैंने एक्सपेरिमेंट किया, मेरे पास B पर एक फास्फोरेसेंस इवेंट रजिस्टर हो रहा है. सिंपल इक्वेशन उसने देखी और देखा कि यार इस इक्वेशन में Vx आ रहा है. सो हाउ डज वन फाइंड Vx? ठीक है, हाउ डज वन फाइंड Vx? एक मिनट, कैन एनीवन गेस व्हाट थॉमसन डिड? मेक सम गेस. एनीवन? देखो Vx फाइंड करना है ना. अब देखो इलेक्ट्रॉन नीचे की तरफ डिफ्लेक्ट हो रहा है. इज देयर सम वे टू रिवर्स दिस डिफ्लेक्शन? change the polarity, okay, but then the spot will go up. What if we want to keep the electric field the same and move the phosphorescence back to A? Apply a magnetic field. And apply a magnetic field such that the magnetic force on the particle is in the upward direction. So then what Thomson did was superimposed on this arrangement an electric field, a magnetic field such that the force is in the upward direction. Okay, so he had a magnetic field that is pointing out of the plane. These are negatively charged particles, so the particle will go up. So now you have two crossed fields, an electric field and a perpendicular magnetic field, and he adjusted the strength of that magnetic field B such that this spot went back to A. Now when the spot goes back to A, this means that the magnetic force acting on the electron is the same as the electric force. And what is the magnetic force? Magnetic force क्या है? E V X P. Okay? And this magnetic force is exactly equal to the electric force. Which means that Vx is equal to E over B. E is equal to the voltage divided by the separation B. So now one can put this value of Vx back into Vy. E V L M D Vx is simply V So this is Vy, and it's now independent of Vx. Now how does one find the charge to mass ratio? The charge to mass ratio can now be found by noting. Alright, let's redraw the figure. यहाँ तक बात समझ आ गई? Clear नहीं यहाँ तक तो? There is an upward magnetic force which is being counteracted by a downwards electric force, and the beam of particles goes undeflected. So one adjusts the magnetic field such that the beam goes undeflected, and whatever that adjustment is done appears as the magnetic field. Now one has to find the charge to mass ratio. What we also know is that if the magnetic field is switched off, the phosphorescence appears at this point B. So if you look at the diagram above, which I can redraw, this is the undeflected path. This is the point B. This velocity is Vy and this velocity is Vx. One can measure this angle theta. That is how far downwards has the beam gone. And this theta, tangent of theta, will be given by Vy over Vx. And if theta is small, that is the deflection is small, and this is approximately equal to theta. So now this expression tells us that Vy equals theta Vx. So this equals theta Vx. One can measure theta. And one can insert the value of Vx here and find what the charge to mass ratio should be. So the charge to mass ratio is theta times Vx over LB, theta over LB, and Vx is simply V over dB. The charge to mass ratio turns out to be theta V L B square D. So this is how he found out the charge to mass ratio of the electrons. All these parameters are experimentally measured. Theta is experimentally measured. The voltage applied on the plates is experimentally measured. The length of the plates is known by construction. The magnetic field is known by construction, is known by design. One can measure the magnetic field. You measured the magnetic field in the freshman lab using Hall sensors, but Thomson also measured it. D is the separation between the plates by virtue of construction. So all these experimental parameters are within our grasp. We can measure them, and when we measure them, we can find the charge to mass ratio of these electrons. And no matter what gas you use in the discharge tube, exactly the same charge to mass ratio appears. So that these particles belong to all matter. These are universal particles. Now we know that these are fundamental particles of all matter. No matter what element you're talking of, electrons are the same.
How did we measure theta from a curve?
Just theta does not depend on being a curved surface. If this surface is flat, it's the same theta. Theta is just this angle. It doesn't change if you use a curved surface or a flat surface. ठीक है. अब ये बात याद रखो, थॉमसन ने चार्ज ऑन एन इलेक्ट्रॉन फाइंडिंग किया था, उसने चार्ज टू मास रेशियो फाइंड की थी. ठीक है. लेकिन एक और उसने खूबसूरत बात ये देखी कि जब एक्सपेरिमेंट होता है इलेक्ट्रोलिसिस का, फॉर एग्जांपल इन द इलेक्ट्रोलिसिस एक्सपेरिमेंट, इफ वन यूजेस HCl, हाइड्रोक्लोरिक एसिड, व्हाट हैपेंस ऑन द एनोड? Hydrogen is on the cathode, hydrogen gas is released. So one can measure the mass of the hydrogen gas versus the charge that flows through the electrolysis experiment, and one can find the charge to mass ratio for the hydrogen atoms. So the charge to mass ratio of these electrons, which Thomson measured, was about approximately 1 into 10 raised power 11 coulomb per kilogram, which is close to our present value. And the charge to mass ratio that was found from electrolysis experiments for hydrogen was about 10 raised to power 8 coulomb per kilogram from electrolysis experiments, which showed that the particles that Thomson had recently discovered were about 1,000 times lighter than the hydrogen atom, which is simply a proton. So he could guess what the mass of these particles was. Okay? So Thomson had discovered electrons. That's the moral of the story. And it was Millikan in a series of experiments performed by Millikan and his students Geiger and Marston, who calculated the charge on an electron, who measured the charge on an electron. And those experiments were performed over years, दिन रात काम करके, और हम 3-4 घंटे भी मुश्किल से बैठने लेबोरेटरी में. So experimental physics requires a lot of patience, a lot of hard work. These experiments were performed over days and nights, over several years, and Millikan finally found out the charge on an electron, which is very close to our present value, and he showed that the charge is indeed quantized. The particles are discrete, so the charge must be quantized. So this is how the electron was discovered at the turn of the 20th century. ठीक है, तो इलेक्ट्रॉन की बात हमने कर ली, फोटॉन्स की बात हम पहले कर चुके. अब एटम में इलेक्ट्रॉन के अलावा कुछ और भी तो है, न्यूक्लियस. The question of stability arises. An atom is electrically neutral. So, if an electron has a negative charge, it must somehow be balanced by an opposite positive charge inside the atom. Could I repeat what I said? देखो, अगर एटम न्यूट्रल है और हमें पता चल गया कि इलेक्ट्रॉन्स आर नेगेटिवली चार्ज्ड, because we know what direction the deflection is occurring, the particles must be negatively charged. So once we've established that the electrons are negatively charged, there must be some positive constituent inside the atom as well. And that is what Rutherford did in 1911. So now we're going to look at Rutherford's experiment in 1911. And he discovered what is now called the nucleus. अब हम देखें सब एटॉमिक फिजिक्स की दुनिया में हमने कदम रख लिया. Now we have opened the door of the atom, entered the atom itself. We've seen that the electron exists. We've discovered the electron. We know that the electron is now a particle. It has a known charge. The charge is quantized. The charge to mass ratio is known. And now we're looking at what else makes up the atom. तो रदरफोर्ड को सहारा था उसके दो बहुत अच्छे स्टूडेंट्स थे, गाइगर और मार्स्टन, तो दिन रात काम करते थे उसके पास. जी, ये दरअसल रदरफोर्ड के स्टूडेंट थे, और रदरफोर्ड के एक स्टूडेंट एक पाकिस्तानी भी थे. किसी को नाम पता है उनका? उनका नाम है रफ़ी चौधरी. और वो रफ़ी चौधरी, उन्होंने कैम्ब्रिज यूनिवर्सिटी में रदरफोर्ड के साथ पीएचडी की. फिर वो उस वक्त तो पाकिस्तान नहीं बना था, 1920s 30s में वापस हिंदुस्तान आ गए, आज़ादी के बाद पाकिस्तान आ गए. और यहाँ उन्होंने, आपने देखा होगा, गवर्नमेंट कॉलेज में सेक्रेटरीट के सामने एक ऊंचा सा टावर है. सेक्रेटरीट के सामने एक बिल्डिंग है जो गवर्नमेंट कॉलेज के पास है, ठीक है, उसके ऊपर एक ऊंचा सा टावर है. उसके अंदर उन्होंने पार्टिकल एक्सेलरेटर लगाया था रफ़ी चौधरी ने. उसको वॉल्टन कॉकक्रॉफ्ट टाइप का पार्टिकल एक्सेलरेटर था, जिसे गवर्नमेंट कॉलेज की हाई टेंशन लेबोरेटरीज कहा जाता था. अब उसका नाम सेंटर फॉर एडवांस स्टडीज इन फिजिक्स है. तो रफ़ी चौधरी के एक शागिर्द पाकिस्तानी भी थे, और सॉरी, रदरफोर्ड के एक शागिर्द पाकिस्तानी भी थे, ठीक है. तो इस लिहाज से पाकिस्तानी कनेक्शन भी है रदरफोर्ड का. एनीवेज, व्हाट वाज रदरफोर्ड्स एक्सपेरिमेंट? रदरफोर्ड का एक्सपेरिमेंट इतना एक्साइटिंग था कि उसका अंदाजा नहीं किया जा सकता. और जब वो गाइगर और मार्स्टन ने रिजल्ट्स अपने सुपरवाइजर को रिपोर्ट किए, भागे भागे आए रदरफोर्ड के पास कि हमने ये देखा. तो रदरफोर्ड ने चीख मारी खुशी से और उसने कहा, वो जो रिजल्ट्स आए उसके बारे में उसने कहा, इट इज लाइक शूटिंग अ कैनन बॉल ऑन अ टिश्यू पेपर एंड एक्सपेक्टिंग द कैनन बॉल टू कम बैक. यानी इतना इम्प्रॉबेबल इवेंट उन्होंने देखा कि एक कागज के टुकड़े पर एक तोप का गोला फेंकें और एक्सपेक्ट करें कि तोप का गोला रिफ्लेक्ट होके वापस आए. इतना हैरानकुन वो एक्सपेरिमेंट था. और वो एक्सपेरिमेंट क्या था? लेट्स टॉक अबाउट दैट एक्सपेरिमेंट. सॉरी, क्या कनेक्शन था? देखिए, आइडिया तो प्रोफेसर का होता है और उसके साथ वो मुआविन होते हैं. तो प्रोफेसर स्टूडेंट्स को कहते हैं लेबोरेटरी में काम करो. प्रोफेसर ने और भी बहुत से काम करना, पढ़ाना भी होता है आपको, ठीक है. ये वजह. तो आइडिया, एक्सपेरिमेंट करना ही सिर्फ नहीं होता, उसका आइडिया सोचना और उसको इंटरप्रेट करना रिजल्ट को, वो सारा काम रदरफोर्ड ने किया, इंटरप्रेट किया रिजल्ट्स को और एक फॉर्मूला बनाया कि दिस इज व्हाट वी एक्सपेक्ट। ठीक है, तो रदरफोर्ड की कंट्रीब्यूशन को आप बिलिटल ना करें किसी बात पे। अच्छा, व्हाट वाज रदरफोर्ड्स एक्सपेरिमेंट? Rutherford's experiment was basically like this. Now the experiment goes like this. One has a lead box, a box made of lead. Okay? This is lead. Inside the lead there is an element, radon. Now radon is a radioactive element. It emits alpha rays. So these are alpha rays coming out, and we know that an alpha ray is just a helium nucleus. It's doubly positively charged. Radioactivity had been discovered. Okay? Marie Curie had performed a large number of experiments on radioactivity. She had discovered radon. So women can also enter the field of physics. Marie Curie ने radioactivity radon discover कर लिया था और radioactive है element, इससे alpha rays खारिज हो रही हैं. Now the alpha rays are helium nuclei, doubly positively charged, and they are falling on a very thin gold foil, a very thin gold foil, and they're passing straight through, and here you have a zinc sulfide screen, a phosphorescent screen. When a particle strikes this screen, a flash occurs. Another particle comes in, a flash occurs, and behind this screen there is what is called a traveling microscope. Now one can observe the flashes through this microscope. So just recognize the patience that is required for performing this experiment over long periods of time. So what can be done is one rotates this microscope through an angle theta, just as we've done in Compton effect. So one fixes the position of this microscope at a particular theta and counts the number of flashes per unit time, changes the value of theta, counts the number of flashes per unit time, and so on, for over a long period of time, and the entire assembly is in vacuum. The entire assembly is in vacuum. Could anyone tell me the reason why? Deflections. The alpha particles can ionize air, and when ionization takes place, if there is water vapor, the water vapor can condense on the ions and form a cloud. This is how particles are detected, in fact, in the nuclear physics laboratory. These are called cloud chambers. So air really has to be pumped out of this experiment. You need to have vacuum, and vacuum technology was flourishing at a rapid pace. देखो फिजिक्स सिर्फ किताबों में नहीं मिलती. फिजिक्स करने के लिए आपको लेबोरेटरी में भी जाना पड़ता है, वर्कशॉप में भी जाना पड़ता है, मजदूरों के साथ बैठना पड़ता है, मिस्त्रियों के पास बैठना पड़ता है, गिल्ड्स में जाना पड़ता है. तो this is what physics is all about. It's not only just reading the textbook. It's a very fine form of human civilization and human perfection. Now this is the arrangement of Rutherford's experiment. Now what happens is that most of the particles most of the alpha particles go straight through. Most of the alpha particles go straight through. Now let's draw a picture of the atom. And this picture was also inspired by Thomson. थॉमसन एक मॉडल दिया था एटम का जिसे कहते हैं प्लम पुडिंग मॉडल. और ये 1898 में थॉमसन ने प्रेजेंट किया था. प्लम पुडिंग मॉडल सिंपली ये था कि एटम इज जस्ट अ होमोजेनियस बॉल which is negatively charged और इसके अंदर पॉजिटिवली चार्ज्ड सेंटर्स हैं छोटे छोटे और होमोजेनियसली डिस्ट्रीब्यूटेड. जिस तरह आपको केक बनाते हैं उसके अंदर रेजिन्स डाल देते हैं, ठीक है. हमारे पाकिस्तानियों को पुडिंग का नहीं पता, लेकिन चूंकि ये थॉमसन ने ये लफ्ज़ इस्तेमाल किया हमें भी. तो ये प्लम पुडिंग मॉडल था एटम का कि एक नेगेटिवली चार्ज मास है और उसके अंदर पॉजिटिवली चार्ज सेंटर्स हैं चार्ज को बैलेंस करने के लिए. नाउ व्हेन एन अल्फा पार्टिकल व्हिच इज अ डबली पॉजिटिवली चार्ज न्यूक्लियस फ्लो थ्रू दिस एटम, it will scatter minutely and go straight through. It will scatter minutely. देखो ये positively charged है, it will be repelled. It will be slightly repelled by this center, positively charged center, but largely it will go undeflected because there is a homogeneous soup of negative charge as well. So this is an alpha particle which is doubly positively charged and it goes largely straight through the atom with little or no deviation. So we have a large number of particles coming in, seeing the atom in the gold foil, and they pass largely undeflected. So this was the idea with which Rutherford started the experiment, and he proposed that most of the alpha particles will go straight through and they will be scattered from the positive and negative charge inside the atom, but the angular deviation will not be very large, at the most about 1 degree. That is, most of the alpha particles will lie within the range of 1 degree from the undeflected part. That is, most of the particles